We're going to look at the application of the Gibbs phase rule, which is here, where what we're interested in is how many variables, how many degrees of freedom do we have in a system. So we're looking at the phase rule for the case there's no chemical reaction. And when we talk about variables, keep in mind we mean intensive variables. This is a very important aspect of the phase rule. Cannot use it to tell us how much of a given phase we have. We can use it to determine if the concentrations, for example, or the mole fractions are fixed when we have fixed temperature and pressure. So C is the number of components, the number of chemical compounds in the system. So number of components. P is the number of phases. And then the degrees of freedom means the number of variables that we can have control over that are independent. For example, temperature, pressure, mole fractions of a phase. These are the type of variables that we're talking about. Number that we can specify before the system is completely defined. So if we determine that the degrees of freedom is 2, that means we can specify 2 things, for example, temperature and pressure, and then the system is completely defined. So what we want to do is apply this to phase diagram. In this case, it's a case where we're looking at temperature on the y-axis and the weight percent of tin in a lead tin system, and so we have liquid at the higher temperatures and then various solid phases. So alpha is a region where indeed tin and lead mix together, uniform alloy. Beta is a similar region that's a high tin content, complete mixture. This is a high lead content. This is a region where alpha and the liquid phase are in equilibrium, so we have 2 phases. Any point in here really corresponds to so much of the solid phase and so much of the liquid. Exactly the same now for this region, except the liquid's in equilibrium with the high tin content solid. In this region we have corresponds to 2 solids, so much of the alpha phase and so much of the beta phase. So let's look at some point here in the alpha phase and determine how many degrees of freedom we have. So we're going to look at the alpha phase. So the number of phases is 1. Number of components is 2. And so if we apply phase rule then to this system, we have 2 components, we have 1 phase. It says we have 3 degrees of freedom. So the particular diagram that we're looking at is constant pressure. So for the alpha phase we have 3 degrees of freedom before all the intensive variables are specified. One of those degrees of freedom is pressure, and we've already specified that in the diagram we're looking at is at a given pressure. So second one would be temperature, and then the third would be, well, let's say the concentration or the weight fraction, the weight percent of tin. So those would be the 3 independent variables. If we pick 200 degrees, we still have a range of concentrations that are possible in the alpha phase. Pick this point at 200 degrees, then we specified a concentration, pressure, and a temperature. Those are 3 degrees of freedom. All intensive variables are now specified. So this is intensive variables that we specified for that system. Let's look at another point in the phase diagram. Let's look at somewhere in this region, the alpha plus beta phases. So remember what this corresponds to is a mixture of phase that's rich in lead and this solid phase rich in tin, and a given point determines how much of each of those 2 phases we have. So we'll look at a point in that region of the 2 solid phases and again apply the phase rule, number of degrees of freedom. Still have 2 components. We now have 2 solid phases. This says we have 2 degrees of freedom. One of those is pressure, which when we specify a particular diagram, that's at a fixed pressure. So we only have 1 more variable. And for example, if we specify temperature, then we fixed all the intensive variables. And so if we look at this diagram and say we're at about 150 degrees, then that specifies concentrations of the alpha phase, concentration of the beta phase. Does not tell us how much of each of those phases we have. For example, if we're at this overall composition, then we have much more of this tin-rich phase than we do of the lead-rich phase. But phase rule doesn't tell us anything about amounts. Phase rule is telling us about intensive variables. We can fix pressure and, for example, temperature, or pressure and concentration of a phase, and then everything is fixed. So the phase rule says we have 2 degrees of freedom in this region where there are 2 solid phases in equilibrium.
Hi friends, in this video we cover what is the iron carbide phase diagram. Then let's start. In their simplest form, steels are alloys of iron and carbon. The FEC phase diagram is a fairly complex one, but we only consider the steel part of the diagram up to around 7% carbon. Phases in Fe3C phase diagram. Alpha ferrite, solid solution of C in BCCFe. Stable form of iron at room temperature. The maximum solubility of C is 0.022 weight%. Transforms to FCC gamma austenite at 912 degrees Celsius. Gamma austenite, solid solution of C in FCCFe. The maximum of C is 2.14 weight%. Transforms to BCC delta ferrite at 1395 degrees Celsius. Is not stable below the temperature, 727 degrees Celsius, unless cooled rapidly. Delta ferrite, solid solution of C in BCCFe. The same structure as stable only at high temperature, above 1394 degrees Celsius. Melts at 1538 degrees Celsius. Fe3C, iron carbide or cementite. This intermetallic compound is metastable. It remains as a compound indefinitely at room temperature, but decomposes, very slowly, within several years, into alpha Fe and C, graphite, at 650 to 700 degrees Celsius. FEC liquid solution. Classification. 3 types of ferrous alloys. Iron, less than 0.008 weight% carbon in alpha ferrite at room temperature. Steels, 0.008 to 2.14 weight% carbon, usually less than 1 weight%. Alpha ferrite and Fe3C at room temperature. Cast iron, 2.14 to 6.7 weight% carbon, usually less than 4.5 weight%.
The experiments. The first experiment is the diffusions in solid. Okay, so we have some gel inside a test tube, and then we put a piece of copper sulfate. Copper sulfate is blue in color, and you need to know the colors of copper sulfate. Okay, so make sure that you remember the colors of copper sulfate. Because in exam they will ask you what's the colors of copper sulfate. So copper sulfate is blue in color. Okay. After a few days, we found that the blue colors of the copper sulfate initially is a piece of crystal here, and this copper sulfate, the blue color spread, okay, spreads to almost the whole gel. Okay. This is something very strange. Why? Because we know that on the surface of the Earth, we have gravitational pull, right? So if we have gravitational pull, then the blue color, it should go down, but it shouldn't go up, right? But the fact is that this blue color, it go up, okay, spreads to the whole gel. So this happen is because diffusions. It's because of diffusion. So how this occurs? Now let's say we have the gel here. Let me use the green color to represent the particles of the gel. So this is the particles of the gel. Okay, this is the particles of the gel. And then this is the particles of the copper sulfate. Okay, this copper sulfate. So what happened is that the particles of the copper sulfate, it dissolve in the gel, okay, and then it move randomly. Randomly means that it move in a direction which cannot be determined. Random directions, okay, it move here and then bounce back and go down and go here, okay. That is called the random motions. Okay, random means that cannot be predicted. Random means cannot be predicted. So the directions of the motion cannot be predicted. It moves in randomly. Okay, so go up and then bounce back. Okay, hit this one and go bounce. Okay, and go up. And due to these random motions, the random motions of all these particles of the copper sulfate. So the blue copper sulfates move up to the gel. And this process is called diffusions. Diffusions is from high concentrations of copper sulfate. This is high concentrations. Okay, this area, the concentrations of the copper sulfate is high, and this area, the concentration is lower. Okay, so the particles, it will move from high concentrations to low concentrations. Okay, so this process is called diffusions. There are a few questions in the chat rooms. And so say, can you repeat the change in concentrations? Okay, now that is not a change of concentrations. That is for diffusions. There's one thing that you need to know is the particles, it diffuse from high concentrations to low concentrations. So at this area, the concentrations of the copper sulfate is high. This area, the concentrations of the copper sulfate is low. Okay, and the particle, it will move from high concentrations to low concentrations. Okay, even though this is against gravity, against gravity. Gravity, according to the pulls of the gravity, it should go down, but it go up, because this part, the concentration is high, and this part, the concentration is low. Okay, so in your definitions, you must state that diffusion is a process resulting from random motions of molecule by which there is a net flows of matter from regions of high concentrations to a regions of low concentration. When you define this, you must state this. It must be from regions of high concentrations to the regions of low concentrations.